Sometimes one single idea comes along and just changes everything. That's what we're talking about today. We're diving into this one research paper from 2017. The title? It sounds pretty simple, but what was inside, man, it completely rewrote the rules for AI. It's the reason we have the powerful language models we see all around us today. So, to really get why this was such a big deal, let's just start with something super simple. Think about how you're processing my words right this second. How do you, read a sentence?
I mean, you don't read it like this, do you? One word at a time. Come on, no way. If you did that, by the time you got to the end of a long sentence, you'd have no clue how it even began.
Nope, your brain just gets it. It sees how all the words connect to each other, like all at once. It's like this instant web of meaning, and you understand the full context just like that. And that right there, that's exactly where AI used to get stuck. And that brings us to the big moment. Back in 2017, a team of researchers at Google posed this really simple but honestly profound question. What if we could teach a computer to do the same thing, to understand language just like a human does? All right, let's get into it. To really understand why that question was so game-changing, we've got to rewind a bit. We need to look at what AI looked like before 2017. And this huge, massive wall that everyone in the field kept running into. So back then, the go-to models for stuff like machine translation were these things called recurrent neural networks, or RNNs for short. And the key thing to know about them is that they worked sequentially. They processed everything one little piece at a time, in order. So here's what that actually looks like. An RNN would say, read the first word of a sentence. Okay, then it'd read the second word while trying to remember the first one, then the third while trying to remember the first two, and on it goes. Just imagine trying to read a really long novel that way, one word at a time. You'd completely forget what happened in chapter 1 by the time you got to the end, right? So this whole approach led to two gigantic problems. Problem 1, it was painfully slow. I mean, you can't speed it up by doing things in parallel. You're stuck going one by one. And problem 2, it was just forgetful. The path, the distance between a word at the very beginning of a long sentence and a word at the very end was just too long. The model would lose the thread. Okay, so the researchers weren't just stuck. They come up with a pretty clever patch to deal with that whole forgetfulness issue. And this patch was an idea called an attention mechanism. It's kind of like giving our slow, one-word-at-a-time reader a whole set of highlighters. So as the RNN was trying to translate a word, this attention add-on let it look back across the entire original sentence and ask, okay, which of these words are most important for the word I'm working on right now? It could instantly focus on the important stuff, no matter how far back it was. But, and this is the key part, it was still just a band-aid, a workaround. Yeah, the attention thing helped with the memory for sure, but it was still bolted onto that same slow, sequential engine. The core problem, the real bottleneck, the speed, it was still there. And this is where the whole story just takes a sharp turn. The team at Google saw this setup, this slow engine with a cool but limited add-on, and they asked a question that was, honestly, totally radical for the time. Right there, in the abstract of their paper, they just put it out there. They said, hey, we're proposing a new, simple network architecture called the transformer, and it's based only on attention mechanisms. They were getting rid of that whole one word at a time thing entirely. They weren't just tuning up the old engine, they were tossing it in the junk pile. The question was basically this: what if you could just throw out that slow sequential part? What if you could build the whole thing using only that powerful highlighter, that attention mechanism? What if you could make a model that looks at every single word and how it relates to every other word, all at the exact same time? And the answer to that question was the transformer, a totally new kind of architecture built from scratch with one goal in mind: see everything all at once. The engine driving this thing is a mechanism called self-attention. And this is the magic trick. For any given word it's looking at, self-attention allows the model to weigh the importance of all the other words in the sentence all at once. It literally calculates a score for how much it should pay attention to every other word. And this creates this incredibly rich understanding of context in just one single shot.
But they didn't stop there. They took it a step further with something called multi-head attention. So instead of having just one self-attention process, the original paper used 8 of them, all running in parallel. Think of it like a team of specialists, all looking at the same sentence. You've got one expert with a blue highlighter looking just at grammar, another with a green one tracking how subjects and verbs connect, maybe a third with a yellow one looking at style. Then you combine all their notes, and suddenly you have this super deep, multi-layered understanding of the text.
And this table really shows you the why. This is the technical breakthrough in a nutshell. The old way, the recurrent way, was what computer scientists call O of N. Basically, the longer the sentence, the more steps you had to take. It gets slower and slower. But self-attention? That's O of 1. That means it's a constant number of operations. It takes just one complex step, whether the sentence is 10 words long or 100 words long. This is what made it lightning fast. And it gave it a perfect instant memory of the whole sentence. So look, it was a really beautiful, elegant idea in theory. But did it actually work in the real world? Well, the results, they weren't just good. They were absolutely stunning.
They tested it on a standard benchmark, English to German translation, and the transformer got a blue score, which is a measure of quality, of 28.4. Now, that number might not mean much on its own, but what it meant was a new state-of-the-art record. It didn't just edge out the previous best models, it completely demolished them.
And here's the real kicker. It wasn't just better, it was way, way more efficient. It got these record-breaking results using just a fraction of the computational power that the older models needed. So you got better translations for less money and in less time. That was the real game changer. So when you boil it all down, there were these 2 huge, undeniable wins. First, the quality was just superior. It set new records. And second, the speed was incredible. Because it was designed to be parallelized, they could train a massive model in just 3.5 days on only 8 GPUs. I mean, that kind of speed was just unheard of back then. So this paper really wasn't just another tiny step forward. By throwing out that old sequential method and betting everything on attention, it created a whole new foundation for the entire field. It was a true paradigm shift. It showed everyone a new way forward that was better, faster, and way more powerful.
So yeah, the transformer completely revolutionized machine translation. But its real impact? Oh, it was so much bigger. That exact same architecture, the one that was built to translate sentences, it turned out to be the perfect engine for AI that generates sentences. Back in 2017, the big question was, okay, it transformed translation. What's next? Well, today, we're all living inside the answer to that question.